This is the last chapter of grade 7 free math for our curriculum. So, remember that there is a final exam and that you should review all the stuff you learned before and, of course, this time in this chapter. Before that, you should do all your homework and so on. All right, this chapter is about probabilities. First, before we can assess the chance of something happening, you gotta have an idea of how many ways can something happen. So when you make an organized list of outcomes, it is called a sample space, and this can help you determine the total number of possible outcomes for an event. For example, let's say an electronics store offers a Model 2020 processor with a choice of 2 monitors and 2 printers. Draw a tree diagram to determine how many different computer systems you have if only these components are considered. Honestly, this should probably be a Model 2020 computer tower or a laptop core, like the core components beside the monitor. Although, for laptops, the monitor kind of just decides the size of the case. So perhaps that's not the best example. Oh, well. Okay. Anyway. So the rest of the computer is Model 2020. So because it's called a processor here, we'll call it a processor. Okay? And the monitor can be 15-inch or 17-inch. And then for each of these, the printer can be inkjet or laser. Ink, laser. So, this shows that 4 different systems are possible because in the end it's 15-inch ink, 15-inch laser, 17-inch ink, 17-inch laser. Well, I mean, yes, you could also put Model 2020 in front of each of those, but I kind of abbreviated. Okay, so 4 systems possible. Okay, so let's say we have an event M. Big M in this case. It can occur in little m ways, and is followed by event N, which can occur in little n ways. The event M followed by the event N can occur in m times n ways, presuming that they are independent, or at least that event M does not affect the number of ways that event N can occur in. Technically, it could still affect the chance of each of those outcomes for n. Like say, oh, a woman is giving birth to twins. Okay, the first twin was a boy. The second twin could still be a boy or a girl, even if we don't know if it's a monozygotic twin or a dizygotic twin. So we don't know whether they're identical or fraternal. Fraternal means that they're as related as any other set of siblings, which means that there's a chance that you could have different sexes among the twins, whereas monozygotic, identical twins, they are always 2 males or 2 females, barring developmental abnormalities. Okay, so if the first twin is, say, a boy, it will affect the chance of the second twin being a boy or a girl, because there's a chance that it's monozygotic, and there's a chance that it's dizygotic. I mean, compared to if the first twin is a girl, the chances are very different. But the number of outcomes is still the same. So the fundamental counting principle is being applied to the number of outcomes, not the probabilities, unless these events are independent. So if the first event does not affect the chance of the second event, various outcomes. So, example 2, a lot combination is made of 3 numbers from 0 to 39. How many combinations are possible? So, for the first number, how many choices do we have? Well, we have 0 to 39. Is this 39 choices? No, because 0 is also included. 0 is the first choice. 1 is the second choice. 39 is the 40th choice. Number 1, 40 choices. And it's the same for number 2 and number 3. Okay, how many combinations are possible? So we have 40 times 40 times 40, so 40 to the third power combos. Because you have 40 choices for your first number, multiplied by 40 choices for your second number, that's already 1,600 combinations, and then 40 choices for your third number. So 64,000 combinations. Okay, let's do some exercises. A museum tour includes a boxed lunch which contains a ham, beef, or veggie sandwich and an apple, orange, peach, or pear. An equal number of all lunch combinations are available for each tour. Draw a tree diagram to determine the number of outcomes. Okay, look, tree diagrams, you usually see them drawn horizontally. However, it is also possible to draw a tree diagram vertically. So what happens if we do our tree diagram vertically? Well, yeah, it's pretty obvious why I'm going to be doing it vertically. And it's largely because ham, beef, or veggie is H, B, and V. Whereas the fruits are not distinct, so it doesn't take up that much space. Ham, beef, and veggie. But if we did it vertically, we'd need like 12 rows, which gets kind of awkward. Okay, ham, beef, and veggie. Ham, beef, and veggie. Ham, beef, and veggie. So, this would be fruit. And sandwich. Well, next, let's use the fundamental counting principle to find the number of possible outcomes. We roll a number cube twice. Well, 6 times 6, because a number cube refers to a 6-sided die. And we roll it twice, which means 6 outcomes for the first row times 6 outcomes for the second row is equal to 36 outcomes. Now what happens if we toss 6 coins? Well, that's 2 to the 6th power, which is equal to 64 outcomes. So this is because the number of possible outcomes of each toss is not affected by the previous tosses. Each toss has 2 possible outcomes. Okay. Probability of compound events. The probability of 2 independent events can be found by multiplying the probability of the first by the probability of the second. So let's say we have 2 number cubes, one red and one blue, rolled. What is the probability that the outcome of the red number cube is even and the outcome of the blue number cube is a 4? Well, P red even, blue 4 is equal to probability of red even times the probability of blue 4. Which means we're looking at a number cube is numbered 1 to 6. So even is 1/2. And the blue number cube getting you a 4 is 1 in 6. So this is 1/12. Now if two events A and B are dependent, then the probability of both events happening is the product of the probability of A and then the probability of B given A occurs. The probability of B after A is written this, by the way. B given A. So the probability of AB is equal to the probability of A times the probability of B given A. Now let's say there are 8 black socks and 6 white socks in a drawer. If one sock is taken out without looking and then a second is taken out, what is the probability that they both will be black? Well, on your first draw, you have just the chance of black. And then multiplied by the chance of black given black, which is going to be, I mean, you could also write B and B, like A and B up there, but, well. So, the probability that it's going to be black is 8 out of 14. We assume this is completely random. I know, guys, we're going to stuff 6 huge white socks in there and 8 tiny black socks. No. Yeah, this is supposed to be actually random. Probability problems are supposed to be random unless otherwise stated or unless they're clearly not. I.e., your sampling, for example, is biased. Like going to a fish store and then asking people what their favorite pets are. Like a store for pet fish and aquarium supplies. Yeah, that sounds a little bit anti-non-fish. So the probability of another black sock, given your first one is black, is 7 black socks left out of 13 socks left. Okay, so 7 by 8 is 56, and this is over 13 by 14, which is 13 by 14 is 182. Maybe we should have canceled out 2's beforehand. Oh well. So, and on top we would be left with 4 times 7, which would be 28. Let's do some exercises. A card is drawn from a deck of 10 cards numbered 1 through 10, and a number cube is rolled. Find each probability. So the probability that you draw an 8 on the card and roll 2, this is equal to P8 times P 1d6 equals 2. Because P2 would start looking a little bit confusing considering they're both rolling for numbers or drawing for numbers. 1d6 is used in gaming terminology for 1 6-sided die. 1 die, 6-sided. if you want to be specific to the abbreviation. So P8, the chance that you got 8 is 1/10, and multiplied by 1/6, which is equal to 1/60. Probability of two even numbers would be P even card, and multiplied by P 1d6 equals even. In this case, it's just 1/2, or specifically 5/10, multiplied by 3/6, or 1/2. So we're looking at 1/4. Now, if we have two prime numbers, what are the prime numbers between 1 and 10? Oh, we have 2, 3, 5, 7. Okay, then. That means we're looking at probability of prime between 1 and 10. That's going to be 4/10 multiplied by the probability of prime between 1 and 6, which would give you 3/6. And of course, you can cancel this to give you a 5 and a 2, and you end up with, oh, these also cancel, so it comes out to 1/5. The probability of 7 and an odd number, that's going to be the probability that you get 7 on the card, which is 1/10, times the probability that you get an odd number on the die, which is 3/6, or just 1/2. So, this leaves you with 1/20. Now, let's say we have two numbers less than 4. Well, the chance of the first one being less than 4, because it's numbered 1 to 10, that's going to be 3 in 10 multiplied by 3 in 6, or 1/2. So, we're looking at 3/20. Now, the chance of two numbers both greater than 5, well, the first one you have 6 to 10, which is 4/10 multiplied by, well, you only got 6, which is 1 chance in 6. So this is 2, this is 5. And you can also cancel that for a 3. So 1 in 15. Now let's say we have some pencils in a jar. Once a pencil is selected, it's not replaced. Find each of these probabilities. The chance of getting a red and then a yellow equals the probability of red multiplies the probability of yellow given red. So, the probability of red is 5 out of 15 pencils. 15, and the probability of yellow, well, there's 6 yellows left out of 14 remaining pencils, which will give you, well, this comes out to 1/3, but then this cancels out with this to give you a 2, which cancels with this for a 7. Yeah, well then. This is 1 chance in 7. The chance of getting 2 greens is the probability of green multiplied by the probability of green given green. Okay, that means the chance of the first green is 4/15, and the second green is 3 left out of 14. This is, of course, going to cancel to a 5. And some quick canceling will give us 2/35. Okay, now what about green and then yellow? Well, that's the probability of green times the probability of yellow given green, which is going to be 4/15. Times yellow, there were how many? Oh, there were 6 yellow pencils. Okay, so that's 6 left out of 14. And we know that we can do some canceling. 7. So we end up with 4 over 35. P red and then green. So this is P red multiplied by P green given red. And the probability of red is 5 over 15. And green given red, oh, that's 4 greens out of 14 pencils remaining. So we're looking at 1 over 3, and then 2 over 7. So you're looking at 2 over 21. Experimental probabilities are obtained by actually doing the experiment and seeing what shows up. If they are too far away from experimental probabilities and you have done a big enough number of trials, then you could potentially say, oh, the theoretical probability is wrong. Or that it's appreciably wrong. Like if you throw a die 6 million times, you will probably discover that since dice are not perfectly symmetrical, yeah, dice don't actually have a chance of 1/6 of landing on each face. But the error should be negligible enough that we can approximate for our everyday purposes. On the other hand, if you throw a die 10 times, it's perfectly normal to end up having a number just not show up even once, even though you'd expect it to show up at least once. Well, that requires the law of large numbers, where the experimental probabilities should approach the actual theoretical probabilities. And if your actual theoretical probabilities that are being approached are not the same as the theoretical probabilities you had before, that means your previous theory was probably wrong. Okay, let's say Juan is conducting an experiment to find the probability of getting 0, 1, 2, or 3 heads when tossing 3 coins on the floor. The results of his experiment are given here, and the total is 2, 2. 3 plus 3 is 6, plus 9 is 15, plus 10 is 25. Now, based on the results in the table, what is the probability of getting 3 heads on the next toss? Well, the probability of 3 heads, experimentally determined, was equal to 3 over 25. Specifically, this is actually supposed to be number of outcomes with 3 heads over total number of outcomes. Whether you use little t or big T may vary by convention. So, based on the experimental probability, how many times should Juan expect to get 3 heads in the next 55 tosses? Expect. This means that we don't have to get a whole number for our expectation. It's the number of trials multiplied by the probability of your outcome, which means you're looking at 55 tosses times 3 in 25, which will give you cancel this, and you get a 5 here, and then 11 over here, so 33 over 5, which is 6.6 times. So his distribution of the times he gets 3 heads in the next 55 tosses, according to the experimental probability, should be centered around 6.6. What is the theoretical probability of getting 3 heads on a toss? Well, P3H would be equal to PH to the third power, which is 1/2 to the third power, so 1/8. This is the theoretical probability. Now let's say we have a spinner game in an exercise, and it spun 100 times. Red came up 50 times, green 30 times, and blue 20 times. We'll tabulate this. So the table looks like this, the outcomes and their corresponding frequencies. What's the experimental probability of spinning green? Well, that's probability of green is equal to number of green outcomes divided by the total, which is 30 over 100. So 3 in 10. Now, based on the results, how many green spins would you expect to occur in 300 spins? Well, our expectation for green is equal to the number of trials multiplied by the probability of green. And since we don't have a theoretical probability, we'll go with our experimental, which is, well, there's 300 trials multiplied by 3 in 10. Okay. This should leave us with 90 green spins. Alright, if we're going to solve a problem, sometimes you gotta guess and check or act it out. Yeah, this is something that they teach in the curriculum around here. So we also have to kind of know that it exists, even though math is the best way to act it out because it requires less stuff. Like say, you don't need to prepare these different square tiles. Okay, suppose you have a red square tile, a blue square tile, a green square tile, and a yellow square tile. How many different ways can you arrange the tiles to make a larger square? I got a question, guys. Are we allowed to rotate this larger square freely? Or are we allowed to flip the larger square over? Because guess what? Red, blue, green, yellow, and red, blue, green, yellow, let's just rotate it. And if you're allowed to flip in different ways, you very quickly run out of combinations. So, assuming that no flips or spins means 4 choices by 3 choices for the second tile times 2 choices for the third tile times 1 choice for your last tile equals 24 ways. Of course, if you're allowed to flip or spin, this very, very quickly changes everything. For this question, I have a question. What does it mean by different pairs of regular polygons? Does it mean like 2 triangles, 2 squares, 2 hexagons, 2 octagons? Or does it mean an ordered pair, as in you can have a 3-sided and a 13-sided shape, a 4-sided and a 12-sided shape, and so on? We're going to go with this means strictly pairs. Pairs of the same polygons, which is usually the context that you get when you talk about pairs of something. Shapes. The side count ranges from 3 to 8. So we have how many choices? 6 choices. because 3 is your first choice. So it's actually 8 minus 2 equals 6 choices of polygons. Well, polygon pairs. Now suppose you want to buy something that costs 75 cents. If you use exact change, how many different combinations of nickels, dimes, and quarters can you use? Well, in this case, you really actually do kind of have to act it out. So, quarters, dimes, and nickels, and you would just make a table. So, first option is that you use 3 quarters. Okay, and then you can get rid of one of your quarters and use 2 dimes and a nickel. Or you can use 1 dime and 3 nickels, or 2 quarters, 0 dimes, and 5 nickels, and 1 quarter. And what if you used all dimes for the other 50 cents? Oh, you got 5 dimes, 0 nickels, 1 quarter, 4 dimes, 2 nickels, 1 quarter, 3 dimes, 4 nickels, and of course 1, 2, 6, 1, 1, 8. And what do you do when you run out of space on a table? Well, here's what I generally do. I start a new column and put an arrow that says go up. So Q, D, N. Now, what's left? 1 quarter, 0 dimes, and 10 nickels. And then there's 0 quarters. How many dimes? 5, 4, 3, 2, 1, and then 0. None of these have any quarters. Okay. 6 dimes, that would be 3 quarters. 5 and 5, 4 and 7, 9, 11, 13, 15. So, how many combinations is this? Well, you got 8 here. And then you count this, another set of dimes is from 0 to 5, which is 6. Total 8 plus 6 plus 1, 2, 3. 3 plus 1, which is equal to, well, 3 plus 1 is 4, and then you add 6. 4 plus 6 is 10, plus 8 is 18, and this is combos. Let's say we have a math class and they're playing a game. They're using a number line on the floor. Player unknown starts at 0 and moves forward 8 numbers on their first turn and moves backward 6 numbers on their second turn. If this pattern continues, how many turns will it take for them to move forward to 18? So for every 2 turns, 2 turns moves up 2 numbers, right? Yeah, but for every odd turn, they jump forward, which means to have a jump up by 8, reach 18, you have to start on 10. So it takes 10 divided by 2. 10 divided by 2 equals 5 pairs of turns. Turns to end on 10. And then, if you want to jump up by 8, so on turn 11, they reach 18 because they jump forward by 8. Alright, back to probabilities and data in general. If you have information and you can't use it, it's pretty useless. So how can we use information? Well, we can use sampling to predict the population. A representative sample is unbiased, so it represents the entire population. It does not favor parts or part of the population over other parts. A biased sample does skew your data so that you get an incorrect representation of the population. For example, if you're trying to determine the favorite dog breed of people who enter dog shows, you can survey every 5th person, so this is random, entering a dog show. This is unbiased. However, if you want to survey the spectators at a dog show for what sort of pet they prefer, I assume they're at a dog show for a reason, i.e. they like dogs. So this would be very biased. Alright, let's do some other examples. Like say we have 50 students at our school surveyed about their favorite cookies. 16 preferred double chocolate cookies. 14 preferred chocolate chip, 12 preferred peanut butter, and 8 preferred oatmeal. What percent of students prefer double chocolate cookies? Well, 16 over 50 is equal to 32%. Because it's equal to 32 over 100. And what is a percent? Oh, it means per 100. Now, if the students order 500 boxes of cookie dough, how many boxes should be chocolate chip? Well, 14 over 50 were chocolate chip, so you're talking about expectations for chocolate chip, which is equal to the total number of things, in this case boxes of cookie dough, multiplied by the probability of chocolate chip being preferred, which is going to be 500 times the probability of chocolate chip being preferred was 14 over 50. So you cancel out the 50. And you end up with a 10. Okay, so you end up with 140 boxes. Boxes. That's the unit involved. You expect to order 140 boxes of chocolate chip according to the data that you gathered. Of course, 50 students is probably not a great idea if your school is large enough that you're actually expecting to reasonably sell 500 boxes of cookie dough or make enough cookies out of those. Anyway, describe these samples. To determine if the tomatoes in 4 boxes stacked on a pallet are not spoiled, the restaurant manager checks 4 tomatoes from the top box. This is biased. And it's also a convenience sample because the manager chose those tomatoes because they were convenient. Convenience samples are generally biased. Why is this biased? Well, maybe the top box was put on the stack later, because people generally don't take away the bottom box first or put in the bottom box last. People generally take from the top and put things on the top. So who knows how long the tomatoes in the lower boxes have been there. A random survey of some students for fast food preferences showed that 6 prefer hamburgers, 6 prefer chicken, 3 prefer hot dogs, 3 prefer pizza, and 2 prefer tacos. What percent prefer hot dogs? Well, the total is how much? Oh, 3 plus 3 plus 2, which is 8, plus 6 plus 6, so plus 12. Total 20. 20. So, 3 over 20 is equal to 15%. Preferring hot dogs. I find this really interesting. I mean, I get why you would prefer chicken, because if the chicken you're eating has bones in it, you can be at least reasonably sure that it came off of some manner of dead bird within the last 150, 160-ish years, i.e. since refrigeration was invented. Okay. I wonder, though, why so many prefer burgers to, say, pizza. Oh well. I mean, pizza is pretty popular last I checked. Oh well. So 120 students will attend the 8th grade picnic. How many hot dogs should be ordered? Well, that's expectations for hot dogs. Expectations for hot dogs is equal to the number of overall things that you expect multiply the probability of hot dogs. So the number is 120 students, and the probability of hot dogs is 3 over 20. So that's 6 times 3, which is 18. Hot dogs should be ordered. Now there's something important here. Assuming each person eats one hot dog. This is, of course, a very, very, very sketchy assumption depending on the size of the hot dogs. After all, imagine if we did this for pizzas. Whoa, you should order 18 pizzas for... How many people are interested in eating pizzas? And how big are these pizzas? Yeah, same idea here. I mean, tacos is relatively straightforward because giant tacos are a little bit awkward to eat. Burgers, even there, the size variation is huge. Tacos, yeah, they also vary in size. And chicken, I really hope you aren't going to say ordering however many chickens equal to the number of people interested in having chicken. Yeah, that would go kind of awkwardly, I think. And it also wouldn't be very fast food either. Well then, that's it for this section. It's also it for this chapter, and also it for this course. Remember that there is a final exam, so please review everything you've learned and do all your homework, and review your homework for that matter, so that you can do well on the final exam. See you another time.